Hey everybody, welcome back. So we have our third Power Series video, and we are going to try and tackle the differentiation and integration with Power Series. So I wanted to start off with just a quick review of some of the things that we've already done that might play a role in today's lesson. And so the biggest thing I think we've done, or started with rather, with Power Series was studying the radius and interval of convergence, right? And what exactly does that mean for a power series, and how the interval of convergence really relates to how a power series sort of maps to a known function or potentially maps to a known function. And when I say mapping to known functions, I'm talking about having the exact same outputs for the exact same inputs, right? So the infinite polynomial outputs matches a function's outputs for specific input values. All right. And so what we did from there was we started to look at some well-known functions. And the big four that we've talked about so far are sine, cosine, e to the x, and 1 over 1 minus x. Those are the big four that we absolutely need to know sort of moving forward. Because what we did with those, beyond finding their intervals of convergence, and remember that really the only one that has a strange interval of convergence is 1 over 1 minus x, right? So that was in between -1 and 1, not including -1 and 1. The other three have an infinite radius of convergence. And so the reason why we worked with those first was, number one, they're easy patterns to pick up on. So their actual power series were easy to create or come up with without having to do a whole lot of extra work. But beyond that, if we have sort of these four big functions, we can do a lot with just these four to come up with power series representations of a whole host of other functions that are either a combination of two to all four of these potentially. And we did that by adding, subtracting, multiplying, dividing, and then finally we did some composition. And so we saw with that, technically we come up with an infinite number of power series for an infinite number of series, just knowing these four. And so that really led the way to how I think powerful, no pun intended, power series can actually be for helping us. And we talked about sine of x squared or cosine of x squared or e to the x squared, even for that fact, eventually having to differentiate, integrate, particular integration. How if we can have a power series representation of those functions, I'm actually able to integrate those functions unlike I was before. So that's just a really quick review. This is what I really want to try and get into today. We want to be able to use differentiation and integration, again, to create different power series of other functions as well, right? So think about all the ways that we could manipulate sine, cosine, e to the x, 1 over 1 minus x, and then potentially differentiate and or integrate those. So we'll talk about specific functions today a little bit. But then we'll also just kind of practice with just general power series that may or may not map or relate to a uncertain known function, just for lack of a better term, kind of like random power series that I've either found or that I've created, just to get a feel for how you can differentiate and integrate and what that process is like. So here's a quick look at sort of how it works. And I think this is a really nice parallel to something that you already know really well. And I hope this gives you a good idea moving forward, at least for differentiation to start with. Okay. Throughout the video, I do have some try on your owns. I am going to encourage you to pause the video. I have the answers right here on the video, which I'll sort of release as we go on. But again, really do your best just to even just take 3 to 4 minutes and just try the try on your own really quickly. Just jot them down and see how you're doing with them. All right. Okay. So let's jump into this one. Let's look at the case of sine to cosine, right? So what do we know right off the bat, sort of in the beginning? Well, we know that the derivative of sine is definitely cosine, right? That's something we learned first semester, maybe even first month of last year. And so this is something really well known to us. The other thing we also know at this point, this is from the previous video, right, is that sine's power series is represented right here, okay? So if I know that the derivative of sine is cosine, then I should be able to take the derivative of this power series and get to cosine's power series. That's the whole idea, right? They're supposed to work exactly the same and represent the exact functions. So I should be able to differentiate this power series and get to cosines. Very quick reminder. Hopefully this is not an actual reminder to you. Hopefully you just know this definitely off the bat, right? Power rule for polynomials. Bring down the exponent, subtract 1 from the original exponent, and that's your new exponent, right? So here's this the power rule. And so here's what's really nice about integrating and differentiating power series is that these are the only rules you need to know. I'll give you the reminder for the power rule for integration once we get there, but if you know these two power rules, you're in really, really good shape, okay? The one thing I'm just going to stress here, and maybe just a little bit as we move forward, is that these power rules and everything that we do is with respect to x, right? Or with respect to the variable that makes the series a power series. And so any other variable, any n's or, whatever it might be, does not get included in this power rule. I only want to take the exponent of the variable that I'm differentiating with respect to and bring it down, right? N's are variables in our series, but if I'm differentiating with respect to x, I'm not going to mess with those at all. They're basically constants or coefficients at this point, okay? All right, so let's jump in here. So down here, I've got the derivative of sine x, which I know is really the derivative of sine's power series, right? So these two match up exactly. And so all I'm going to do is use the power rule, right? So here's my differentiation with respect to x. My exponent is 2n plus 1. Well, I'm going to bring that right in front, right? So I'm basically bringing that right in front of the x, which is normal. I'm going to take 2n plus 1, which is my original exponent, subtract 1 from it. The negative 1 to the n and the 2n plus 1 factorial, those are coefficients. Again, it's not an x variable, it's an n variable, so they stay the same. And then I'll just simplify. Okay, so this really isn't too bad at all. I'm telling you, this seems complicated, but you've done a lot of the hard legwork to get to this point, and now it's really not too bad. So I just want to note a couple things, right? So the first thing is that the exponent, right, changes because I'm subtracting 1 from the 2n plus 1. So it just becomes 2n, which is good because that's cosine's power series. And then this 2n plus 1 gets simplified with this first 2n plus 1 and the 2n plus 1 factorial, right? Remember 2n plus 1 factorial really is 2n plus 1 times 2n minus 1 times 2n minus 2 times 2n minus 3, so on and so forth. So this 2n plus 1 up top simplifies with this, the first 2n plus 1, the first term in the 2n plus 1 factorial. And so what's left is 2n factorial, right? Because if I just get rid of the first term here, I'm left with 2n times 2n minus 1 times 2n minus 2 times 2n minus 3, so on and so forth. So I'm left with 2n factorial. Simplifying factorials becomes really important here for this reason, right? You have to be able to simplify this accurately to get to the most simplified version of your answer. And so we get to cosine's power series, right? So that's actually pretty cool. A lot of times some teachers I've seen videos that kind of show you sine and then wait to give you cosine until you get to this part, just because it's kind of like a nice reveal of, oh, you can do this and look at this, it works. But it does work definitely. And so we're good to go. All right. So hopefully that was kind of a nice simple first example for you. You're just doing the power rule, which is nice. It's really easy. Let's move on to something a little bit different. So this is one of those just sort of random general power series that just to practice with. This was actually on the 2015 exam, I believe. This wasn't this exact question, but it was pretty close. There's a lot more tied to it, which I'm hoping to either show you or give you some AP free response questions that go a little bit deeper into this stuff. But this power series was used on an actual AP exam at one point in time. So it is a Maclaurin series because it's centered at 0. And what they did was they gave you the Maclaurin series and then give you a couple of terms, and then there's the general term again, right? So they give you the first 3. What I want to be able to do is basically take that and write the first 3 non-zero terms and the general term for the derivative of that power series. Okay, so again, I don't know the function that it represents, if it even represents a known function, but I can find the derivative all the same, right? I don't need to know that this is sines power series or cosines power series or whatever it might be. I just need to be able to work with the exponents and use the power rule effectively and then simplify effectively. So I'll take the derivative of the power series that I'm given and I'll just go through the process, right? So I will, just here, sorry. Yep. So I've got x to the n. I'm going to bring down the n in front. I'll subtract 1 from the exponent. I notice that I have an n to the first on the top and n to the first on the bottom. I can simplify. I can cross those two out, right? So this one goes and this one goes. And then so I'm just left with no denominator and just this negative 3 to the n minus 1, x to the n minus 1. A further simplification, and this just creates something really nice, which I'll reveal in just a second. I noticed that they have the exact same exponent. And so if two bases have the same exponent that are multiplied together, I can combine those two to get a singular term to that one singular exponent. And so the answer to just the derivative, right? So this represents f prime is negative 3x to the n minus 1. And so this would be your answer for just the general term. And at this point, you can do one of two things. So I left this down here as the answer because the question does ask us for the first three non-zero terms and the general term. So you can do this in one of two ways. You can find the general term, which we just did, and then literally just plug in n equals 1, n equals 2, n equals 3, and see what the first three terms are, right? You can just write them out. Or again, we are differentiating this infinite polynomial, which means I'm differentiating the individual terms. This is actually kind of a nice way to make sure that you did it correctly, actually. So it's kind of a double check. And so if you look here, right, if you plug in n equals 1, n equals 2, n equals 3 into this power series right down here in the orange box, you would get 1, negative 3x, and then positive 9x squared. Hopefully that works for you. Definitely try it. However, you can also get these first three values by looking at the first three terms that was given to you. And if you just differentiate this, take the derivatives of these three individual terms, you should get the exact three terms that you got from your differentiation series, right? So derivative of x is 1, boom. Derivative of 3x squared over 2, bring them the 2's cancel. It's a negative. I just left with negative 3x. Boom, good to go. 3x cubed, bring down the 3. 3 times 3 is 9. Subtract 1 from the exponent, 9x squared. Boom, good to go. All right. Looks like I added a fourth term here. If you want to go out to the fourth term, that would be it, right? And if you found a fourth term up here, you could differentiate there. So again, not too bad, right? Two different ways there. If you know the power rule, this really isn't too bad at all. Okay. I do want to just point something out. So this isn't necessarily something you would need to know for any assessment or quiz that we would have. This is a AP level recognition, definitely. And by that, I mean an AP exam level recognition. I think this is kind of one of those stretch questions that if you get this, you're really seeing sort of the big picture. And if you don't, that's okay for now. That's why I'm showing it to you so you can start to recognize and see some of this stuff, right? Does anybody recognize what type of series this is and maybe what function this series, the one we just found, actually represents? So give it a second, pause the video, and just look at it and think about how do you get from one term to the next and how that might be important. Okay, if you had a chance to do that, what do I notice about this series? I put this fourth term here to help you out a little bit with it. So how do you get from 1 to 3 to negative 3x? And then from negative 3x to positive 9x squared? And then from positive 9x squared to negative 27x cubed? Hopefully you're seeing a pattern a little bit, right? 3, 9, 27. I'm just multiplying by 3. So I've got this sort of 3 to the nth power almost going on. And then the x's also jump up, x to the 0, x to the first, x to the second, x to the third. And so really what I have here is actually a geometric series, right? Remember, the geometric series is just the infinite series from 0 to infinity of x to the n. Well, what I did here was compose, I adjusted, I manipulated the geometric series so that the common ratio was negative 3x. I'm starting at n minus 1, which is fine. You can start geometric series at other exponents other than just n. And so really what this function, or what this power series represents, is the function 1 over 1 plus 3x, right? Because here is 1 over 1 minus negative 3x, a over 1 minus r, right? So my a value is 1. It's my first term, which lines up. And my common ratio is negative 3x. And so this whole thing added up, the sum of this geometric power series is a over 1 minus r, or 1 over 1 plus 3x. So again, that's higher level, definitely. But if you saw that, you kind of got there, awesome. If you understand it now, just as awesome. Okay. If you have questions about that, please let me know. All right, let's move on. Okay, so here's a try on your own. So definitely, like I said, pause the video at this point, see if you can get there. Really what I'm doing is basically the same thing as the last one. I'm not asking you to interpret it any further than just finding terms in the general term. You've got a random power series there, and I want you to find the first three non-zero terms and the general term for f prime. Biggest difference here, right, is that it's no longer a Maclaurin series. It is a Taylor series because it's centered at 1. But remember, if you were to take the derivative of x minus 1 to some exponent, I would still just bring down that exponent. It is technically a chain rule, but the derivative of the inside, the derivative of x minus 1, is just 1, so that doesn't change anything. Okay, see how you do. All right, I'm going to reveal the answer, and we'll talk about it, and then see how you did. Let me just get rid of it. So here is the answer. So the first thing I did was just write out basically the same thing. So I've got my coefficients, which is negative 1 to the n plus 1, 2 to the n over n. That's my coefficients that were already there. I'll bring down my n in front, subtract 1 from the exponent. The n's simplify from one another. And so then I get this power series. All right, so hopefully you were able to get there. And then at that point, I just plugged in n equals 1, n equals 2, n equals 3. And if you plug in 1, the only thing that stays, is the 2 to the n, which is 2 to the first. This becomes a positive 1. This goes away because it's 1 minus 1, which is 0. So this just goes to 1. So your first term is 2. And then you plug in n equals 2, and you can start to see it come to life a little bit. All right. All right. So hopefully you're able to get that. Let me know if you have questions. Okay, so let's go into integration. What we will see is both definite and indefinite integration. There are times where you'll definitely be able to just leave a plus c there for indefinite integration. In that case, it's really nice and easy because, again, you're just using the power rule, right? So here's your reminder, right? You add 1 to the exponent and divide by that same exponent, and then you have your plus c. If you don't need to find c, then great. Then that's a plus c there. A lot of times, though, you would like to find plus c because, again, you're trying to find either a function or if this relates to a function, you're trying to use it to approximate a value. And so having a plus c there doesn't help you approximate anything because you don't know what c is. So a lot of times we'll have to find the plus c. It's not too difficult, and I'll show you how to do that. But we are going to do both definite and indefinite integration. So the definite integration that we'll work with, and I do want to make this reminder, is what happens when we have a variable bound, right? So one of the bounds, typically the upper bound, is a variable. In this case, it's going to be x. Well, inside of the integral can't be the same variable, right? So typically we use a t there. If you want to think back to the fundamental theorem of calculus, right, where we did the derivative of the integral from 0 to x of f of t dt, we just replaced the inside variable with a t instead of an x, so that in the end, I was left with f of x, right? So x was my finishing variable. You'll see that work out here in just a second, but you'll see that the power series variable will change to a t instead of an x, and that is simply because we're making the upper bound an x, and in the end, the finishing power series will have a variable of x as we know it, okay? But look what happens here. So I have from 0 to x of some constant or coefficient a, right? And that could be any term that we pick, times t to the n dt. So the t to the n is really the part that's being integrated. I would add 1 to the exponent, so it would be t to the n plus 1 divided by n plus 1. But then I would plug in the upper bound, right? F of b minus f of a. So the t would then turn to an x. So x to the n plus 1 over n plus 1. I still have that a out in front. And then I would subtract f of a, right? So I'd plug in 0. Well, what will happen here is the second part, the minus f of a, will hopefully always disappear for us because we're going to evaluate it in such a way that I'm just left with the actual power series part of it. Okay. And so you'll get that where it's just the actual function piece. So the variable there, no actual number. And I'll explain sort of why we do that. Okay. But those are just 2 reminders of how things work, and those are going to be really helpful. So here's my first example. I'm connecting it to a known function. And so the known function that I want to try and find a power series representation for is the natural log of 1 minus x. Something that you have to either recognize or just note, that's why we're going over it, right? So you kind of recognize how this works, is that I know that the integral of 1 divided by 1 minus x is equal to the negative natural log of 1 minus x plus c. The reason I'm pointing that out is because, well, in order to get to the power series for the natural log of 1 minus x without actually going through all the steps of taking derivatives, plugging in a center value, matching all them up, hopefully finding some pattern that works, is I already know the power series for 1 over 1 minus x. And if I know the power series for 1 over 1 minus x, and the integral of 1 over 1 minus x is related to the function I'm using, I want to find, just instead of a positive, it's negative, then all I need to do is integrate 1 over 1 minus x's power series. And I can get to my desired function pretty quickly, actually, without doing a whole lot of work and creating a power series the long way. So I'm going to base this whole thing off of the geometric series, 1 over 1 minus x, the x to the n power series. Okay, so let's look at it. So based off of that, here's what I know. The natural log of 1 minus x is equal to the negative integral of 1 over 1 minus x, right? So just go back really quickly. It's because I know that the integral of 1 over 1 minus x is negative natural log of 1 minus x. And so I'm just going to put the negative sign to the integral instead so I can get my exact function that I'm looking for. So then that means that the integral here is really just equal to the integral of, the negative integral of the power series that's represented by 1 over 1 minus x. And from there, I just use the power rule. Very nice, right? So I've got x to the n. I'll add 1 to the exponent, divide by that same exponent. And so here is my general form, my indefinite form of the power series that represents the natural log of 1 minus x. So if this was just an indefinite integral, I could stop right here. This is really nice. But again, a lot of times we want to use these power series to approximate values of this function. So having that plus c doesn't really help me. And so how do I get rid of that plus c, or how do I find a value that satisfies that plus c? Really, all this means is I just need some initial value, right? So we've done plus c's before with differential equations, and we just had some x is equal to blank, y is equal to blank. You plug in for x, you plug in for y, and you solve for c. It's just algebra. And really, that's really all we're going to be doing as well. Except this time, I get to pick my x value that I'm plugging in. When we're doing this, pick the center value, right? You can pick an x value. You can pick 1, 2, 4, 5. I don't care what you pick, right? But if you pick anything other than the center value, you're causing a lot of problems for yourself. And you'll see why in just a second. The center value for the series I started with and the series I ended with is 0, right? It's not x minus 1 or x minus 2. It's x minus 0 to the n plus 1. So I'm starting, my center value is 0. We want to do that because A, it's going to make life really easy for us in just a second. But B, the center value, without doing the ratio test for convergence, is really the only number or only value that I absolutely am guaranteed that the series converges for. So this input is valid 100% of the time. which is really nice. Okay. So at x equals 0, what happens? Well, my function, the natural log of 1 minus x, becomes the natural log of 1 minus 0. So this is really like your y value almost. It's your output, right? And so I'm just replacing all the x's with 0. And then I also have to do it to the power series that I created. So I'll plug in 0 for x that was up here, right? So that's where that comes from. And now look at it. Well, the natural log of 1 is just 0. So I'm good there. And if I take the infinite sum of 0 to the n plus 1 over n plus 1, the top is always 0. So this whole thing is just 0 itself, right? So this whole infinite series is actually just equal to 0. So I get 0 is equal to 0 plus c, or c equals 0. So this one worked out really nicely. C is gone completely because there was no value for c, especially when x equals 0. And so now I have the natural log of 1 minus x is exactly equal to the negative infinite sum of x to the n plus 1 over n plus 1. Again, just the power series, a little bit of extra work there at the plus c, but overall, hopefully not too bad for you. All right, here's a second example. This is a random one, so I don't have an exact function that this is tied to. And I'm going to do this one just a little bit differently. So instead of using the plus c, I'm going to use sort of a definite integration approach. And the reason I'm doing that is because I don't know the function that this power series represents. And in order to get an initial value to figure out c, I need to know the function to get the output value, get that y value. Since I don't know that, I'm going to use this definite integration approach. And so if I know that a function f has a derivative f prime, and f prime is defined by this infinite series, I need to integrate f prime in order to find the power series for f, right? So there's the fundamental theorem of calculus at work. Integral of the derivative cancels each other out, right? And so I should just get back to the original function. So let's start by actually just looking at the integral of this power series up here, right? 2 to the n, 3n factorial, those are coefficients. Those aren't going to be messed with. Interesting here, right? Because now I have an x minus 1 to the nth. So it's no longer a Maclaurin series. It is a Taylor series. Technically, you're doing u substitution, right? Because I'm no longer just x to the nth. It's x minus 1 to the nth. However, if we make u equal to x minus 1, du is just 1. And so that doesn't really affect us, right? We can use the power rule almost naturally here without really thinking about u substitution. And so you'll see that come into play a little bit here, okay? But in order to find this, I'm going to use this definite integration approach, all right? And again, that's because I can't find the c without knowing the function. So what I'm going to do is take my power series that I have, which is f prime. I'm going to integrate it. I want to end up with a power series in terms of x. So my top bound is going to be x because that's going to be the first value. That's your b value that you plug into f. And that's going to keep my finished series in terms of x. So that's what I want to input as f of b, right? So it's my upper bound. And then the lower bound, I'm actually going to make equal to my center, right? Which is this problem is kind of set up that way. The reason why I'm going to make it equal to the center is because when I do f of b minus f of a, I have to plug in 1 for t or for x or whatever the finishing variable will be. Well, if I plug in my center value, I know that that's going to eliminate every term within that given series that I created. All right, because look here, if I plug in, just ignore this integral for a second and plug in 1 for t, that becomes 0 to the n, which zeroes out the entire power series. And I'm only going to be left with f of b, which is really going to be f of x, which is perfect, okay? So I'm going to take this power series and integrate it. I do that using the power rule. So I'll bring down my, excuse me, not bring down, I'll add 1 to the exponent, so n plus 1, and then I'll divide by that same exponent. So there's my n plus 1 down here, okay? And so here's what I'm left with. I have to evaluate that from 1 to x. And so again, the first thing I do is just replace all my t's with x's. So it's really just this 1t, and t minus 1 gets replaced to x minus 1. And then I would actually have to plug in 1 for t, Well, if I plug in 1 for t, this becomes 0 to the n plus 1, which makes every term equal to 0. And so that's non-existent. That just goes away. And so I could have a minus 0 here if you really wanted to, right? As your sort of f of a. This would be your f of a over here. But again, that's just going to be equal to 0, so that just totally goes away. And I'm just left with this guy right here. All right, so sort of a backdoor way of getting around not knowing the function, but having a power series and being able to integrate. Okay, I think I have some try on your owns to do. And let's see how you do, and we'll go over them. All right, so here's a try on your own. The e to the x, I know that seems silly, right? Because the integral of e to the x is e to the x, and we already have e to the x's power series. But there's kind of a nice flow here with having to find c, because you notice that when you do integrate x to the n over n plus 1, x to the n over n factorial, it's not the same power series, but I know the integral of e to the x has to equal e to the x. So how does a different power series equal the same function? And how does that work out? So I want you to try that. And this one's going to focus on really the process that I did with example 1. So you will have to find the c and plus c. Remember, your ending function is e to the x, because you know that. You know the integral of e to the x is e to the x. So use that to your advantage. And then the second example, the second try on your own, is a more general power series. And I'm using this definite integration technique from 2 to x, right? Because my center was 2, t minus 2 here. So that's going to eliminate that second term. Okay, again, pause video, give it a shot, come back. Okay, let's see how we did. So for the first one, here is my work. So I know that the integral of e to the x is going to be the integral of x to the n over n factorial. Okay. I'll just add 1 to the exponent, divide by that same exponent, and then I still have that n factorial there from the original. Notice that n plus 1 times n factorial is really just n plus 1 factorial, right? So you can simplify that right off the bat. All right, n plus 1 factorial is n plus 1 times n minus 1, so on and so forth, which is the exact same thing. So here and here, those are the exact same values. Okay, so I have this plus c. So now I have to work on finding plus c. Again, we talked about what value of x should you choose. Always choose the center value. It's a Maclaurin series. The center value is always 0. So if I plug in x equals 0, what do I know? Well, I know the integral of e to the x is e to the x. So I can plug in 0 for x. So e to the 0 is equal to the infinite series evaluated at x equals 0, which really just gets rid of this whole part, right? Because 0 to the n plus 1 over n plus 1 factorial is 0 itself. So that whole thing goes to 0. And so now I'm just left with e to the 0, which is 1, equals 0 plus c. 1 equals c. So now I've got c is equal to 1. Oops, sorry, didn't mean to cross that out. C is equal to 1, right? So now, how does that work the same, right? Are they exactly the same? Because I know e to the x's power series is x to the n over n factorial. So how is it also x to the n plus 1 over n plus 1 factorial plus 1? Well, if we look at it, right, I can rewrite x to the n plus 1 over n plus 1 factorial plus 1. I can move this plus 1 out in front, right? Because I'm not plugging in n, or I'm just adding 1 to the power series. So commutative property of addition says I can move that plus 1 out in front. 1 plus the infinite series x plus 1 over n plus 1 factorial. Start plugging in n equals 0, n equals 1, n equals 2, n equals 3. And what do you get? Here's your 1 plus from the beginning, right? So that part right here, here, and here, those are the same values. That's the exact same thing. And the power series actually starts up at x to the first. And then you move to x squared over 2 factorial, x to the third over 3 factorial, which is exactly equal to just x to the n over n factorial from n equals 0 to infinity, which is exactly e to the x. So that does work out, which makes sense because we know the integral of e to the x is e to the x, and so they do have to be equal. Just kind of an interesting process there where I have e to the x is equal to 2 different power series possibilities. Okay, and then the second one was my definite integration case. So I'll set it up. from 2 to x, take my exponent, which is n plus 1, so that becomes n plus 2. If I add 1 to it, I'll bring n plus 2 on the bottom. Not a whole lot of simplification or combination here at all. I do know that I need to evaluate the answer from 2 to x, and so I plug in x for t, and then I also plug in 2 for t and subtract those two values. But if I plug in 2 for t, this whole piece goes away, and I'm really just left with replacing t with x. And so here's my power series representation. Okay. All right. Coming down to the end here. So I just want to sort of tie it. So I put it all together here, kind of tie everything together. Why is this useful in connection to what we did last video? And this is the first thing that I really started you out with when we talked about power series, the integral of sine x squared. And I asked you, could you do it? And you thought about u substitution, you thought about partial fractions or by parts, and none of that stuff works. And because there is no analytical way of doing it, just with sine of x squared itself. What we have to do is first create the power series for sine of x squared. So this is what we did last class. I'm not going to go over this fully, but we did learn that sine of x squared is equal to this power series down here. All right, negative 1 in the n, x to the 4n plus 2 over 2n plus 1 factorial. So if I know that this is the power series for sine of x squared, I now know how to integrate power series. So I'm going to take this power series and integrate it, right? And I'm going to do that using the definite integration approach, again, because I don't know the function. There isn't one. I don't know the function integral for sine of x squared. So I can't plug in an initial value. So I'm going to use the definite integration part. If I take the integral of the power series, I'll add 1 to the exponent. I'll divide by that same value. I know I'm saying that a lot, but just trying to make sure I have it in there. And then again, if I plugged in x, I would just replace the t with an x. If I plugged in 0, the whole thing would go away. And so I'm just left here. All right. So if I wanted to find a definite value for sine of x squared, this would be it. This is the power series representation for the integral of sine of x squared. So this infinite polynomial is exactly the same as the integral of sine of x squared. Okay. So then the big question is, okay, well then how do I find a value, right? Let's say I wanted to integrate not just indefinite, but maybe I wanted to do a definite integral from 0 to 5 of sine of x squared or something of that sort. And that's really where we're heading. That's kind of the finishing touches to the power series for us, because what you'll notice is that we can't go out to infinity. We have to stop the power series at a certain value, and we're going to use an approximation technique there. The more values you use, like the more terms you go out to, the better the approximation will be, obviously. But typically we'll only go out to about the 4th or 5th term, and then try and figure out what the error on that approximation is. And so that'll be our finishing touches here. But for right now, we're just kind of finding power series, and then we'll actually use the power series with approximations. Okay. My one final note, this is just kind of a nice piece that makes a little bit less work for us, a little bit less thinking. If I have a power series f of x, so here's the series that f of x is represented by, and I know its radius / interval of convergence is r, then differentiating or integrating that function, that power series, does not change the radius of convergence for the derivatives and integral power series. So the derivative of a power series has the same radius of convergence, and the integral of power series has the same radius of convergence as the original function you were working with. Just a nice little fact there. You can certainly try it with some of them if you want, but it should work. The homework will be on my Malvern. It's just going to be a couple of ones like to try on your own. Hopefully you were successful with those. If not, hopefully you'll be successful with the homework. I'll post the solutions, and I'm available for help. All right. Let me know if you want to talk individually. I'm happy to do that. All right, guys. Have a great day. I'll talk to you soon.